All right. So the purpose of this session is for me to answer questions regarding anything that we've covered up to so far. So that's kinematics as well as beams. I would think that everyone is good with relative velocity as well as resulting velocity. Right? If there are any questions, they should be at this point on projectile motion as well as beams. Right, let's go. Do we have any questions on the floor regarding anything? Hmm, no questions. I think this is going to be a short and sweet one. Hello. So no one has questions about anything.
Hi, sir. Would you be able to do one beams with us, please? Especially for the drawing wise of drawing the diagrams. Because I watched your video, but I would just like you to do another one just for clarity.
Um,
As well as on Moodle, there's no questions, like past questions for the beam, sir. Like you posted on relative velocity and resultant and projectiles.
mm, uh, so for beams, if you're able to do that one, because with beams, if you understand how to calculate reactions applying conditions of equilibrium, so applying conditions of equilibrium meaning if you're able to use the sum of moments to calculate your reactions, you are able to draw the shear force and you're able to draw the bending moment diagram. There's nothing more to it, if we're being honest, right? It's unlike with relative velocity and resulting velocity. There's quite a bit of things, conceptually speaking, that you need to be aware of, right? And also not just the concepts, but there are quite a few variations of problems that you need to be aware of, right? So whereas with beams, either you'll be given the diagram and you're asked to calculate reactions, you're asked to draw the shear force as well as bending moment diagram, right? As long as you're able to do that, that is it with beams. Right, so that is why I didn't post or I didn't upload more problems on beams. Right. Mm, okay. So we have a beam, right? The beam has two reactions. Right. You have a reaction here at A and you have a reaction there at C. Right. The beam, this one in particular has two UDLs, right? And a point load, right? And you're asked to calculate the reactions. So at A and C. So in this case, you're asked to calculate the bending moments at B and C, right? So B and C are probably the most critical points. Right? So hence, they've asked you to calculate the bending moments at B and C, right? Now, the reason for that probably is because um, what is the thing called? Simply supported. What's the other one? What's the other beam? They were simply supported beam aside from the cantilever. On the video, do I mention the types of beams? that we get. I keep forgetting this one.
I doubt you mentioned it, sir, because that is why I'm now confused with your question.
Hmm, what is it being called? So you get different types of beams. You get a simply supported, simply supported beam. A simply supported beam is where you have a beam and you have a reaction at each end of the beam. Right, so call it A, call it B. Right, if you have a beam, right, and it has reactions on either end of the beam, then that beam is known as a simply supported beam. Right? Yes, now I remember. Then you have an overhanging. Yeah, this is the one I'm looking for. Overhanging beam. An overhanging beam is where you have a beam, say you have maybe one reaction there, and then you have another reaction at that point. Right? The point here is that a part of the beam is always overhanging. Right? So this one has different variations. Um, you could also have, say, one reaction at that point and another one there, right? So this beam is overhanging here and overhanging there. So as long as part of the beam is overhanging, then that beam is an overhanging beam, right? Now, the nice thing about it though is that both of these beams, the approach is the same. Right? The approach we take for a simply supported as well as an overhanging beam is the same. Right? And then we get a cantilever. Right? You get a cantilever. That is where you have, say, a wall. Right? So maybe you have a wall here. That's a wall. And then you have a beam. Right? And then you get whatever loads that you get on the beam, be it point loads or a UDL, uniformly disputed load. So there will be a cantilever. Now at this level, right, for NATED, we only cover these three types of beams. Right, to only cover these three types of beams. Now we get more types, like a continuous beam. Right, a continuous beam, though, we do not cover at this level. Are we clear?
Yes, sir.
Now,
Yes.
all of this was to say that the reason why here they want you to calculate the bending moments at B and C is because for a simply supported beam, right, as well as an overhanging beam, the bending moments at the ends of the beam are always equal to zero. Are we clear? Right, for a simply supported as well as overhanging beam, the bending moments at the ends, right, of these beams is always equal to zero. Right, so you are expected, or you are expected at this point, by the time um, you write your assessments, be it your tests or your exam, right, to be familiar with that. If you're looking at a simply supported beam or an overhanging beam, the bending moment at the ends of the beam is equal to zero. That is why, yeah, or that is likely why they didn't ask you to calculate, or they didn't ask for students to calculate the bending moments at A and at D, because we already know that seeing that this is an overhanging beam, then we know the bending moment, right, at the ends of this beam is equal to zero. Are we clear?
Yes, sir.
Yes, sir.
All right. Now, they want us to calculate. So what we are going to do here is we're going to calculate the reactions, right, both the reactions, and then we are going to draw. So we're not necessarily going to follow this sequence of questioning. All right, so we're going to do everything that you need to know under the sun regarding beams. Right, so reactions, shear force diagram, bending moments, bending moment diagram. Are we there? Hello.
Yes, sir.
Right. Now with beams, the first thing you look at is the kind of beam you are looking at. So you're looking at an overhanging beam. That's where you know your bending moments at the ends of this beam are equal to 0. Next thing you look at are the kind of loads that you have on the beam. Right. You have 1-point load, reactions, as well as a UDL. Right. Now with the UDL, with UDLs, because you are not able to use the UDL exactly as it is, you always have to resolve it into its weight. The weight of the UDL we express in terms of a point load, and a point load we are able to use in applying conditions of equilibrium. Now remember that with applying conditions of equilibrium, the vectors that you use must be parallel to each other, right? So the reactions are parallel with the point load, right? But the UDLs are not parallel with the point load. That is why you first have to resolve each of these into its weight. Its weight will be parallel with the point loads. Only then will you be able to apply conditions of equilibrium. All right. So first thing you do is you resolve both of these UDLs into its weight. How do we resolve a UDL into its weight? Right. By taking the magnitude of the UDL and multiplying it with the span of the UDL. All right. For instance, here, the first UDL is 55 kilonewtons per meter. To get the weight of this beam, you simply have to multiply this by the span of the beam, not of the beam, of the UDL. All right, you have to multiply this by the span of the UDL. The span of the UDL here is 3 meters. So you then multiply this by 3 meters. That and that cancels. And what you'll be left with will be expressed in terms of kilonewtons. Now, what is 55 times 3?
165.
165 kilonewtons. This here represents the weight of this UDL. And the weight of the UDL, right, acts at half of its span, right? The weight of the UDL is centered at half of its span. So meaning that seeing that the span of the UDL is 3 meters, half of 3 meters is, so say that is there, this is 165 kilonewtons. All right, so that means we are no longer going to be using the 3 meters, right? We'll be using half of 3 meters, right? Which is 1,5. 1,5 meters. Right. So the weight of the UDL acts at half of its span. So meaning, seeing that the span of the UDL is 3 meters, it means this here is acting at 1,5 from either side of the UDL. Are we clear?
Yes, sir.
Right. Now let's look at the second UDL, which is 15 kilonewtons per meter. We want to resolve this into its weight, so we multiply it by the span of the UDL. Right, the span of the UDL is, this one is also 3 meters. Right, from here to there is 3 meters. So you also multiply this by 3. Obviously that goes. So whatever you get here will be in terms of kilonewtons. Now what is 15 times 3?
45.
What is it equal to?
45.
45 kilonewtons. All right, so this represents the weight of this UDL that's acting there. So you have 45 kilonewtons. right? The 45 kilonewtons is going to act at half of the span, right? So seeing that the span of the UTL here is 3 meters, right? It means that you have 1,5 here, as well as 1, as well as 1,5 there, right? Right. Once you've resolved the UTL into its weight, now you can apply conditions of equilibrium. Why? Because now you have all your point loads that are parallel to each other. Right? So the reactions are parallel with all the point loads. Right. Right. Now let's calculate reactions. Calculating reactions, you apply conditions of equilibrium. Right. The conditions of equilibrium we're going to apply here, right, are based on moments. Right. As far as conditions of equilibrium, we have sum of forces going up is equal to sum of forces going down, right? Or you can simply say the sum of forces along the x-axis is equal to 0, as well as the sum of forces along the y-axis is equal to 0. Now, the one we are going to use here is the sum of moments, right? This one is the sum of clockwise moments about a point is equal to the sum of anti-clockwise moments about the same point. Mathematically, this is expressed as sum of clockwise moments is equal to the sum of anti-clockwise moments, right? So instead of writing a whole story when you've been asked to what the conditions of equilibrium are, you can just express that mathematically. Are we clear?
Yes, sir.
Right. Now, we are calculating reactions A and C, starting with A. So we're first going to eliminate reaction C by taking moments about it. So we say take moments about C. Right. Once reaction C is eliminated, it means you'll only have one unknown, which is the reaction at A. Right. Now you say sum of clockwise moments is equal to the sum of anti-clockwise moments. Right. So we are taking moments about C. So now we have to look at the turning effect each of these point loads has towards C. All right. So if you're taking moments about C, what turning effect would reaction A have towards reaction C or point C? Second?
Clockwise, sir.
Yes. So this one will be clockwise. What about the 165? This point load.
The
This
downward
one,
forces is anti-clockwise, sir.
right, so that one is anti-clockwise. The 45 kilonewtons also is anti-clockwise, right? What about the 120 kilonewtons? Is it clockwise or anti-clockwise?
Anti-clockwise.
Clockwise.
This one will be clockwise, yes. So this one will be clockwise as well. All right, so how you look at it is how each of these, how you look at it is how or what would be the turning effect each of these forces has towards, right, where you are taking moments. So if you're taking moments about C, this will have a clockwise turning effect. This one, anti-clockwise, this one, anti-clockwise, and this one, clockwise. All right, so that's how you look at it. Are we clear? Hello?
Yes, sir.
right? Because with beams, if you don't know how to establish the turning effect each of the forces has towards the points you are taking moments about, that's pretty much it, right? You definitely have to get this part right because everything else is just maths, right? The most important part here is that you establish the correct turning effect each of these forces has towards the point you are taking moments about. So it's very important you know how to do that. That is why I'm asking if we are still together here. Because if you are confused by this part, it's pretty much over. There is no moving on without you having understood how we establish how each of these forces, what turning effects each of these forces has towards the point we are taking moments about. So again, can we move on? Are we clear? Are we together?
So,
Yes, sir.
All right. So under clockwise moments, you have the reaction at A that you multiply by the distance, right, from A to where you're taking moments about, right? You're taking moments about C. So what is the distance from here to there?
6 meters.
So that's 6 meters plus, so the 120 times the distance between the 120 and where we are taking moments about. So that is 1,5. So 1,5 is equal to the anti-clockwise moments, which is the 165 times the distance between the 165 and where we are taking moments about. Now, this is why if you have a UDL, it is important that you resolve it into its weight, right? Once you have resolved the UDL into its weight, you then rework the distances to make it easier for when you are taking moments, right? We know that this is acting at 1,5, which is half of the UDL. So to get the distance from the where the 165, the weight of this UDL is acting, right, to where we are taking moments about, now we know it's going to be this 1,5 plus the 3, which is equal to what?
4,5.
4,5.
So that's 4,5 plus the 45 times the distance between where the 45 is acting, where we are taking moments about. Right, so the 45, again, this will establish that seeing that this is the weight of the UDL, it means this is where it is acting, right? And from here to there is a distance of 1,5. So
Sorry, sir.
1,5,
Just
yes.
a quick question. Yes, sir. In this case, we got the UDL, and then we had to resolve it to its way to the load,
Yes.
and then we got the load from the UDL. In a case whereby you were given just the load, a straight load, do you actually have the distances as well in that?
No, you do not. Like for instance, had you not been given the UDLs and you had a point load of 165 and a point load of 45, you would use that exactly as it is.
So the distance would go straight to 3 meters.
Well, in that case, if the 165 is acting at this point, then this is what you use. Only when, say, the 165 is acting at that point, right? So you would have to use the 3 meters plus the 3 meters. But if it happens that the point load you are given is acting at that distance, right, then you'd have to use the distance that you are given. Similarly with this one, if you look at the 120, right, the 120, we used this distance exactly as it is.
Okay, I got you.
All right. Any more questions? Right. So once this is established, right, how you go about this mathematically doesn't really matter, right? I prefer taking a shortcut from here because, like I say, right, the most important stuff has been established. But from here, it's just math. Right, so to make or to cut matters short, so you're gonna have this, right? You're obviously going to transpose this to that side. This side, it becomes negative, right? So minus that, and then of course you are looking for a, so we divide by the 6. So all of this divided by 6, right? And what you get is the value of a.
130 kilonewtons per meter, sir.
130, comma, no comma.
No comma, sir.
Right, so are we all getting 130 kilonewtons here?
No, sir. I'm getting 105.
All right, let me calculate this as well.
105
You have
kilonewtons.
165 times 4,5 plus 45 times 1,5 minus 120 times 1,5.
105, yes, sir. Sorry, that was my
That's
mistake.
it. Now that's fine. So yes, this is 105. Right, so this is 105. Right, no commas, kilometers. Right, and that's what you have. Once you have this, now you can calculate the reaction at C by eliminating A. And the way you do that is by taking moments about A. So now we take moments about A. Right, so we take moments about A. Right, you are now taking moments about A. Right, so this is where we are taking moments now. Right, you're taking moments about A. So now we look at the turning effect each of these forces has towards the point we are taking moments about, which is A. Right, now looking at this one, will this have a clockwise or anti-clockwise turning effect towards A? The 165.
Clockwise.
So this one is clockwise. What about the 45?
Clockwise.
So that's clockwise. And then C is going anti-clockwise. So this one will be
Anti-clock.
anti-clockwise. Yes. And the 120,
Clockwise.
this one will be clockwise. So every force has a clockwise turning effect, right? Except the reaction at C. Right? Now we say sum of clockwise moments is equal to the sum of anti-clockwise moments. Right? So starting with the 165, the 165 times the distance between 165 and A, which is equal to what?
1.5.
So times 1,5 plus the 45 times the distance between the 45 and A. So from here to there.
4.5.
4.5.
Right. So that's 4,5 plus the 120 times the distance between the 120. So from here to there, which is equal to what?
7.5.
7.5.
7.5.
Right. So 7,5 is equal to anti-clockwise moments, which we have established is only the reaction at C. So times the distance between the two reactions, which is equal to 6. Right. Right. So to get C, C is equal to all of this divided by 6. And what do you get for C?
225.
What do you get?
225 kilonewton.
225 or 125?
225.
225 kilonewtons. Is this right?
Yes, sir. 225.
Right. So once that is done, now you simply say sum of forces going up is equal to sum of forces going down. So now you're trying to see if your beam is in equilibrium. Right. So if your beam is in equilibrium, right, the sum of these forces, in fact, to cut matters short here, let's just say the sum of forces along the y-axis is equal to 0. Right? Is equal to, now forces going down you take as negative, forces going up you take as being positive. Right? Now, when you calculate reactions, right, now in this case, they are both pointing upwards. So the fact that our answers were both positive means that the assumption that our reactions are actually pointing upwards is correct. Right? So A and C are both pointing upwards. Right? All the other point loads are pointing downwards. Right? So down we take as being negative and up we take as being positive. Hence, from here we'll then say forces going up, which is 105 plus the 225, forces going down, so minus 165 minus the 45 minus the 120. This here should be equal to 0. What do you get?
Yes, 0.
Right. So this means the reactions we calculated are likely the correct ones, right? Or the magnitude thereof. Right, saying that when we prove if we test if our beam is in equilibrium, right, using this condition of equilibrium, right, it seems that our beam is in equilibrium. Now you move on to calculating the bending moments. Right, now you move on to calculating the bending moments. Right. Now, in calculating the bending moments, right, in calculating the bending moments, if you haven't been told at which point to calculate the bending moments, so for instance, they say calculate the bending moments at each of the critical points, right? What you should know is that critical points on a beam, right, will be the points that are labeled on the beam, and those points are normally the start and the end of the beam. So each end of the beam, those are critical points. Other critical points will be where you have your reactions as well as point loads, right? So this here is a critical point, that's a critical point, right? And then this one will also be a critical point because there's a point load there, right? And then other critical points would be the start and end of a UDL. So this UDL starts here and ends there. So this is a critical point, that's a critical point. Similarly with this one, the start and end of this UDL, this UDL starts there, it ends there. So this is a critical point and that's a critical point. All right, so critical point where the beam starts and where it ends, so each end of the beam, right, where you have point loads as well as reactions, those are critical points, right? And the start and end of a UDL, those are critical points as well. Now here, they've made things very easy for us. All the critical points are labeled, right? This here is the start and that's the end of the beam. It is labeled. You have your reaction here, you have your reaction there, that is labeled, right? Your beam starts here, ends there, both points are labeled. This one starts here, ends there, both points are labeled. So we have all our critical points labeled, right? And then again, if they haven't specified where you the points at which you must calculate the bending moments, right? You will just calculate the bending moment at each of the critical points, right? Knowing very well that seeing that we are looking at an overhanging beam, the bending moment at this point, which is the start of the beam, or which is one end of the beam, will be equal to 0. And this being the other end of the beam, the bending moment there is also equal to 0. All right. And then when it comes to calculating the bending moments at the other critical points, right, the simplest approach, right, is to consider either forces on the left of that point or forces on the right of that point. And the forces you consider, right, will be the forces that essentially give you, what is this? That essentially give you the path of least resistance, if I can put it like that. And the path of least resistance is will always be where you have the lesser forces or the less number of forces to consider. Like for instance, if you were to calculate the bending moment at B, you can either use forces on the left or the right of B. It doesn't matter which, but the most inconvenient approach would be to choose the side that has the least forces. Right? So between the right-hand side and the left-hand side of point B, which of those sides has the least forces?
Left.
The left-hand side. So as much as you are able to consider forces on the right-hand side, but because on the left-hand side we have the least forces, we are going to consider the left-hand side. Are we clear?
Yes.
Right. Now with bending moments, the approach I teach you guys is very simple because we consider forces going down as being positive, as being negative, and forces going up as being positive. Whether you select forces on the left of the point or forces on the right of the point. Right? If you're doing bending moment calculations, forces going down you take as being negative, forces going up you take as being positive. Right? That's the approach I teach you. I found that this is the easiest approach or the simplest approach. Right? Whether you're considering forces on the left or the right, forces going down you take as being negative, forces going up you take as being positive. Right. Now, let us calculate, say, bending moment calculations. Right. Now we look at the sum of bending moments at B. Right. We said we're going to consider forces on the left of B. Right. Forces on the left of B, you have the reaction at A as well as the UDL. Right. Now, because the UDL, right, because the UDL, seeing that the point B is such that we have to consider the entire span of the UDL. It means when resolving the UDL into its weight, we are going to use the entire span of the UDL, which if we do, we already know we are going to get the 165. So you use the 165 exactly as it is. Right? As opposed to if say we had a point, say here, right? If say this was a critical point or you've been asked to calculate the bending moment at this point, right? Then you would have to resolve the weight of the UDL, but only considering this span. So only considering the 1,5, right? But there is no point there. And seeing that the points that we do have, right, we consider essentially the whole span of the UDL. It means in resolving this UDL into its weight, we are going to multiply it by its whole span. Hence, we are still going to get the 165. So we use the 165 exactly as it is. All right. So we have the reaction at A as well as the 165. The reaction at A is going up. So it's positive 105. So this is 105 times the distance between the reaction and the critical point we're looking at. All right, so this times this span, which is 3 meters. We multiply this by 3 plus, in fact, here, seeing that the force is headed downward, then you simply say, in fact, let's do plus, then make the force negative, right? Just for perspective. So saying that the force is headed downward, we take it as being negative, right? Times the distance between this force and the critical point B, which is the 1,5. So times 1,5. And what do you get?
'Cute. Look at the dining room, and then you carve it.
What is this equal to?
67.5.
Second?
67.5.
Negative or positive?
Positive, sir.
67,5. Remember, this is now in kilonewton meters. Right? And we are also supposed to calculate the bending moments at critical point C. Right? Now, we're at this point, and we can either consider forces on the left or the right. Right? So because we have a least amount of point loads on the right-hand side, we are going to consider forces on the right of C. Right? And forces to consider on the right of C is the 120 kilonewtons. It is headed downward, so you take it as being negative. So it means it's going to be negative 120 times the distance between that force and the critical point we're looking at, which is C. So times 1,5. So times 1,5. Right, so seeing that that's the only force to consider on the right-hand side of C. Right. Now we look at what we get here. Well, what is negative 120 times 1,5?
Negative 180.
Negative 180 kilonewton meters. Right. Right. And then, of course, as discussed, right, at A and D, it's equal to 0 anyway. Right. Now, seeing that we have our bending moment calculations, let us now draw the shear force diagram and then draw the bending moment diagram. All right. So we are first going to draw the shear force diagram. All right, we are first going to draw the shear force diagram. Now, when drawing the shear force diagram, right, it is advisable that you redraw the beam. Right, you redraw the beam exactly as it is. All right, so this is 7,5. All right, you redraw the beam exactly as it is. Okay. Right, so you have your beam. You have a UDL here. Let's just do this. You have a UDL here. Then you have 2, 3, 4, 5. 1, 2, 3, 4, 5. Then you have another one here. And then you have a point load. So you have a point load at this point. Heading downwards, this is 120 kilonewtons. Right, you have a reaction at that point. This is reaction A. You have a reaction there. This is reaction C. Right, and then this point is point D, and point B is somewhere here. Right? Yes. Right. Now, once you have those, you draw a line going downwards, right, from each of the critical points. So you're going to have a line going from there. This line, let's put this line there. So you draw a line going downward from each of the critical points. Right? Now this here is that's 55 kilonewtons per meter. And then this one is 15. This one is 15 kilonewtons per meter. Right? Yes. Right. And then we know these distances. We know that's 3. That's 3. This one is 1,5, right? Yes. Right. From here, you now can draw your shear force. Right. And then after drawing your shear force, you then draw your, what is this? Your bending moment diagram. Are we clear?
Yeah.
Right. So starting with your shear force diagram. Right. In drawing your shear force diagram, you must have a zero line, or you must have a line representing your zero line. Right, so this represents your zero line. So meaning that's 0 kilonewtons. This is for your shear force diagram. Right. Now in drawing the shear force, in drawing your shear force diagram, right, once you are comfortable with drawing your shear force diagram, you won't necessarily have to take the approach I'm about to show you exactly as it is. Right, because once you are comfortable with this, you are able to work it out in your head. Right, but for teaching purposes, this is the approach you would take, right, in drawing your shear force diagram. Right, where you have critical points, right, you draw a section on the right hand side of each of those points. So meaning you are going to draw a section on the right hand side of each of those points. So meaning you're going to have a section there on the right of that point, have a section on the right of this point, a section on the right of that one, and a section on the right of that point. All right, so you have a section on the right-hand side of each of the critical points. All right. And then where you have a UDL on the immediate left of each of the points, right? Or let's say if you have a UDL on the immediate left of a point, then you draw another section on the left-hand side of that point. All right, so obviously there's no UDL on the left, on the immediate left of A, so there won't be a section here. You look at B, there is a UDL on the immediate left of B, therefore, draw a section there. Similarly with point C, because there is a UDL on the immediate left of C, have a section there. All right, if you look at D, there is no UDL on the immediate left of D, so you leave this exactly as it is. All right, so first thing you do is you draw a section on the right of each of the critical points, and then you look at where you have UDLs on the immediate left of the points. And where you have a UDL on the immediate left of a point, you must draw another section on the left of the point. Are we clear?
Yes, sir.
Yes, sir.
All right. Once that is established, let me just check something quickly. So everyone is admitted. Right. Once that is done, now you can draw your shear force diagram by considering forces. Right, you now are going to consider the sum of forces on the left of each of these sections. So meaning, here's your first section. You are going to consider forces on the left, the sum of forces on the left of this section. Now with this one, as far as the shear force diagram or shear force calculations, right, only consider forces on the left of each of the sections, never forces on the right. Are we clear? Right.
Yes, sir.
For shear force calculations or for the shear force diagram, right, you only are going to consider forces on the left of each of the sections. So meaning, considering the first section, we are going to look at forces or the sum of forces on the left of this section. Right, now we only have one force on the left of this section, which is the reaction at A. The reaction at A, remember, is equal to the 105. All right, so you draw the 105. This here is 105 kilonewtons, or this represents the 105 kilonewtons. Right, you must write it there. Are we still together?
Yes.
Right, now
Yes, sir.
those are all forces to consider on the left of this section. So now we go to the next section. Right, getting to this section, we are now going to consider forces between the last section and the current section. The last section and the current section. Bearing in mind that now when you add forces or when you subtract forces, this is your starting point. Are we clear?
Yes, sir.
Yes, sir.
Right, now we are going
Yes,
to
sir.
see that we are looking at forces on the left of this section. We are going to consider forces between the last section and the current section. So forces between the two sections. Right, bearing in mind that your starting point is this one. So whatever force you're going to add or subtract, you're going to add or subtract from this one or to this one. Right, now, what are the forces to consider between the two sections? Right, that will be the weight of the UDL. Right, you consider the whole span of the UDL, right? Because the critical point we are looking at is such that we consider the entire span of the UDL, right? And when we do that, we already know that you are going to get the 165. So you have a 165 at that point, right? So it means the force you are going to consider is the 165, which is the weight of this UDL, the weight of the UDL, which we get when we consider the entire span of the UDL. Right, so now you say the 105, this is going downward. So you say the 105 minus the 165. And tell me what you get.
Negative
Minus
60.
60.
Negative 60. So let's say negative 60, somewhere there. Let's say you have minus 60 kilonewtons. Right, the minus 60 kilonewtons is at that point. Right, now with the shear force diagram, right, wherever you have a UDL, right, wherever you have a UDL on the beam, how we show that is by drawing a diagonal line where you have a UDL. So seeing that in this span of the beam, we have a UDL, the way we show that you have a UDL in that span is by drawing a diagonal line from where we are to where we are headed. Right, so this line is an indication that in this span of the beam, we have a UDL. Are we clear?
Yes.
Yes, yes.
All right, so that's negative 60. Right, so we are done considering forces on the left of this section. So this is our next section. Right, so now we consider forces between the last section and the current section. Right, between the two sections, there aren't any forces to consider. Right, so because there aren't any forces to consider between the two sections, so this one you leave exactly as it is, where it is. It will be a different story had we, say, have a point load at that point. If we had a point load, then that's the point load we'll consider. Or if you had a reaction, right, at that point, then that is what we would consider. But saying that you have nothing, it means you have considered all forces on the left, right, of point B. Right? Now you move to this section or to the next section. And the next section is this one. Right? And then we consider forces between the last section and the current section. Right? The only forces to consider between the two sections, right, are one of the weight of the beam. And again, we consider the entire span of the beam, right? Because the critical point you are looking at is such that we need to consider the entire span of the beam. Now, if we do that, we already know if we say the 15 kilonewton per meter times 3 is going to give us the 45, right? And the 45, we know, is acting somewhere here, 45 kilonewtons. Right, so now seeing that the 45 kilonewtons is headed downward, seeing that it is the B is the weight of the beam of the UDL, so we take it as being negative. All right, so now you say the negative 60 minus the 45 and see what you get.
Negative 105.
All right, it's negative 105. So that's going to be somewhere here, negative 105 kilonewtons. Right, Again, because between these two sections, right, in this span of the beam, we have a UDL. The way you show that is by drawing a diagonal line. So we draw a diagonal line from here to where you have the 105. Right? Right. So you have now considered forces on the left of this section. Now we move to the next section, which is this one. And then consider forces between the last section and the current section. Now, if you look at the two sections, right, how many forces do we have to consider here, if any?
Reaction C.
The reaction C, yes, is 100% correct. The reaction at C, what is it equal to? It is 225 kilonewtons, right? It is headed upward, so you take that as being positive. So now you say the negative 105 plus the 225, which is the reaction at C. And what do you get?
120, so it will take you back to 0. Is that correct, sir?
Sorry?
It's 120.
If it's 120, then it means, right, remember that we are still at point C. So from here, you draw a straight line going up to 120, right? Now, this point is 105, so meaning 120 should be slightly above. So you draw a line going straight up to 120. So here you have 120 kilometers. Are we clear?
Yes.
Right? You have considered all forces, right, on either of these sections. So now you go to the next section, which is this one, and consider forces between the last section and the current section, right? And the only force to consider is which one?
120. D.
The 120, right? The 120 at D. Now it is headed downward, so you take it as being negative. Now, between these two sections, or between these two critical points, there is no UDL, right, in that span of the beam. And how you show that is by drawing a line going across, right? So a line going across is an indication that there is no UDL, right, on the span of, there is no UDL in this span of the beam. Right, so diagonal line means that you have a UDL in this span of the beam. Similarly with this one, you have a diagonal line, so that means you have a UDL in this span of the beam. Now, seeing that there is no beam here, that is why we have a line going straight across, indicating that in this span of the beam, we do not have a UDL. Right, and then you simply say the 120, this is going downwards, so minus the 120, which is equal to 0, and you just draw a line going back to 0. Right, your shear force diagram, as well as your bending moment diagram, they begin at 0 and they end at 0. All right, so this is for either a simply supported beam or an overhanging beam. Are we clear here?
Yeah.
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Right. Now the point or the reason why in drawing a shear force diagram and a bending moment diagram, we first draw a shear force diagram is because the shear force diagram tells us some important information regarding the bending moment diagram, right? Where the shear force diagram is equal to 0, right? The points where the shear force diagram is equal to 0, those points, right? Those points indicate to us possible points where we can expect the beam to experience the most bending. right? So that is to say, the shear force diagram is 0 at this point. It is also 0 at that point, right? So because the shear force diagram is 0 at this point and in this point, it means that it is likely that the beam is experiencing the most bending either between this one or that one. So the beam is experiencing the most bending between this point and this point. Thus telling us that in drawing the shear force, in drawing the bending moment diagram, we need to consider this force, this point. Because as far as where the maximum bending will take place, it will either be between this point or this point. Hence, it is critical that we calculate the bending moment at that point, which will help us in establishing whether the bending moment, whether the beam experiences the most bending at this point or at that point. All right, so that is to say, we have to calculate the bending moment at this point. At that point. All right, it is critical that we calculate the bending moment at this point because the beam might be experiencing the most bending at that point. Why this point? Because remember the shear force, where the shear force is equal to 0, right? Where the shear force is equal to 0, that is where that is where the beam is most likely to experience the most bending. Are we clear?
Yeah.
Yes.
So in calculating the bending moment at this point, right, with bending moments, you consider either forces on the left or the right of that point. In considering those forces, you also have you need to have the distances between those forces, right, and the critical point you are looking at. So meaning we need to establish the distance between this critical point, right, and this end of the beam, seeing that there's much less forces on the left-hand side. Hence, it is convenient for us to consider forces on the left-hand side. And as such, we need to get this distance. Are we together?
Mm.
Right, so this distance, let us call this distance x. All right, so if that is x, now remember that this entire span of the beam is 3 meters. So meaning if we take this distance as x, it means this distance will be equal to 3 minus x. So this distance is 3 minus x. Right, now the easiest way of calculating that distance is by doing this. Right, now if you look at where you have the critical point, right, it is within this entire span of the beam. And within that entire span of the beam, as far as the shear force diagram, you essentially have two triangles. Do you see the two triangles?
Yebo.
Yes.
That's
Yes,
triangle
sir.
1,
So,
this is 2. Do we see that?
Yeah.
just
Right, so you consider or you use those two triangles, right? And all you do is you now say y1, which is the y of the first angle divided by x1 is equal to y2 divided by divided by x2. Right? Now, each of these values we are going to use as distances. Right? And a distance with distances, or let's say distances are absolute. Right? They are scalars. Hence, we do not consider the direction. And seeing that we are going to be taking the y and x value as distances, we are not going to consider a direction. So meaning with y1, we're going to take y1 as that 105. So you have 105 divided by x1. So x1 is the x measurement of the first triangle, which is x. So that's x is equal to y2. Y2 is the y distance, which is 60. So that's 60 divided by the x value of the second triangle,
Say,
which is 3 minus x. Yes.
so do you consider the sign?
So like I said, in calculating the x, right, we take everything as distances, right?
Okay.
Remember that a distance is a scalar,
The scale.
meaning we
Not a
don't
vector,
consider, yes. And then it's only a displacement, or it's only with displacement, seeing that a displacement is a vector quantity, right? That is where we consider direction as well. Right, with
Yes,
this
sir.
ones, seeing that we take them as distances, it means we don't necessarily have to consider a direction.
Sign.
Yes, we don't consider the sign. Right. So the negative 60 you take as positive 60.
Okay.
And then x2, which is the x value of the second triangle, is the 3 minus x. So here you have 3 minus x. And then from here you solve for x. Right. So for x, you'll have the 105 into 3 minus x. So you cross multiply. Multiplying this with that is equal to 60x, right? Then what is 103 times 3?
315.
315, right? Minus x times 105. So 105x is equal to 60x. Right? Then you obviously take this to that side, seeing that this term is negative. Hence, you will have 105x plus 60x is equal to 315. Right, 105 plus 60 is 165x is equal to 315. And then you solve for x here. This is 165 divided by 165. Now you already know that this is tire span is 3 meters. So you are expecting the x value to be less than 3. And what is
Yes,
that
sir.
equal to?
1,909.
1,909 meters. Right? And that becomes your x value. Are we still together?
Yes, sir. Yes, sir.
Right? So you've calculated this x value. So now you can calculate the bending moments. Remember that this is not there. Right, now we can calculate the bending moment at point X by considering forces on the left-hand side. Right? Now, remember that we are considering this span. Right, so we are considering forces on the left of this critical point. Right, considering forces on the left of this point, those forces are the reaction at A as well as the UDL. But now you do not consider the entire UDL. You consider you don't consider the entire span of the UDL, you consider the UDL in this span, which is the value x, right? So now we are going to say sum of bending moments at x, forces going up you take as being positive, right? Remember here you have the reaction at A, which is upward, it is equal to 105. So this is 105 times the distance between the reaction and the critical point, which is this x value. That x value is the 1,909 plus right? Plus, now we consider the UDL, right? But again, we do not consider the entire span of the UDL because you're only looking at this span of the beam, right? Now, how do we resolve a UDL? By multiplying it by its span, right? But because we are only considering this span, it means we are now going to multiply the 55 by this span, which is the 1,909, right? So if you say the 55 times 1,909, right, I get
104.
105.
104,995,
995, yes.
which is in kilonewtons. That is the weight
Yeah.
of the UTL in this span, right? Now, where is the weight of the UTL acting? At half of this span. Half of this span is equal to what? X over 2, x over 2. Agreed?
Yes.
All right, so half of this span is x over 2. So meaning that we know the weight is headed downward, so we take that as negative 104,995 multiplied by the distance from where the weight is acting, which is at half of this span, to where we have a critical point. So times x over 2. X is the 1,909 divided by the 2. Right, and this should give us the bending moment at that x. So it's 105 times 1,909 plus the negative 104,995 times the 1,909 divided by 2. And here I am getting positive 100, comma,
Yes.
227
227.
kilonewton meters. Any questions?
No.
No, sir.
Sorry, sir, can you explain again from the, can you go up a bit? The diagram there, yes. Can you please explain from that x over 2 on one side and then x over 2 on the other side and then all the way
Right.
downwards?
Right. Now, remember that if you have a UDL, right, in order to be able to make use of that UDL, you have to resolve it into its weight, right? You have to resolve it into its weight. But in resolving it into its weight, right, you consider the magnitude of the UDL as well as the span of the UDL, right? In order to be able to resolve this into its weight, you have to multiply this by the span of the UDL. Now, in this case, the span of the UDL we are considering is this one, right? From here to there, which is this X value. We are considering, so we are not considering the entire span of the UDL, but we're only considering this X span of the UDL. Right, so that is to say, in calculating the weight of the UDL in this span, right, we say the 55 multiplied by the span of the UDL, right, which is this X value in this case, seeing that we're only looking at this span of the beam. Are we together there?
Yes, sir.
Right, so now you say the 55, so we say the 55, which is in kilonewtons per meter, you multiply this by the X value. The X value is 1,909. All right, so we said the 55 times 1,909, that gives us the weight of the UDL, which is 104,995 kilonewtons. All right, so we have the weight of the UDL, which is the 104,995 kilonewtons. Now, this being the weight of the UDL in this span means that it is acting at half of the span, because we know that the weight of the UDL always acts at half of its span. So seeing that we are only considering this span, it means this weight of the UDL is acting at half of the span. Half of this span is going to be x over 2, x over 2. Right, half of x. So remember that this entire span is x. Half of that would be x over 2. Are we still together?
It's clear, sir. Yes.
Right, that is important, because in having to calculate the bending moment considering this force, we are going to need the distance between where this force is acting and where the critical point is. Hence, we need this distance, which is x over 2, x being the 1,909. Right, so once that is established, then you consider forces on the left of our critical point, which is the positive 105 times this distance, which is 1,909. That is where this comes from. Right, plus the only other force to consider is the weight of the UDL in this span, which is, seeing that it is acting downward, we take it as being negative 104,995 times the distance between where that force is acting and our critical point. So times x over 2, and x over 2 is 1,909 divided by 2.
Clear, sir.
Right? And then adding all this up, we get 100,227 kilonewton meters. Are all of us together now?
Yes, sir.
Right?
Yes, sir.
Once you've calculated the bending moment at that point, it means you have calculated the bending moments at all critical points. This became a critical point, right? Why? Because the shear force suggests that, seeing that the shear force is equal to 0 here, the shear force suggests that the maximum bending could be taking place at this point. Hence, we need to calculate the bending moment at that point. Right? We already had calculated the bending moment at critical point B, and had also calculated the bending moment at critical point C. Right? So we didn't necessarily need to revisit the bending moment at this point, because we had already calculated it. All right. Now, like I said, the shear force diagram, where it is equal to 0, right? Where the shear force is equal to 0, at those points, that is where the beam is likely experiencing the most bending. And that you will see from your bending moment calculations. Right now, if you look at our bending moment calculations, we know they're equal to 0 at the ends of the beam. Right? We know at point B, it is equal to this. At point C, it is equal to that. Now at this point, point X, it is equal to 100,227 kilonewton meters, which is, as far as the bending moment calculations, this one is the largest, meaning that in actual fact, maximum bending takes place at point X. That is why it is important to calculate the bending moment at this point. If it happens that your shear force diagram crosses over at a point that wasn't previously a critical point. Are we clear here?
Yes.
Yes, sir.
Yes, right. So it means if, for instance, you were asked to determine the maximum bending moment, then you would say here, bending moment max is equal to 100,227 kilonewton
Kilonewton.
meters. Right? Now you can draw your bending moment diagram. Again, with your bending moment diagram, you need to have a zero line. Let's take this as your zero line. Change this one. All right, so you take this as your zero line. All right, so this is where you say you have your 0 kilonewton meters. All right. Now at point A, we know the bending moment is 0. Point B, it is 67,5. All right, it is 67,5. Right. Now, how we, just like with a shear force diagram, all right, so the shear force diagram, there's a way we show that in this span of the beam, we have a UDL. In this span of the beam, we do not have a UDL. Right. Now with a bending moment diagram, how we show that is in the span of the beam where you have a UDL, right? You draw your bending moment diagram in that span such that it is parabolic. All right, you draw it such that it is parabolic. Now, in this span of the beam, if the bending moments at point B are positive 67,5, right? It means that on this part of the beam, the bending moment is increasing. Right, so say that point is going to be, say it's going to be there. Right, so this will be the 67,5 kilonewton meters. Okay, not that point. I've forgotten about this one. Right, now I've forgotten about the where we have our maximum bending moment, which is at this point. Now this point comes before point B, right? So we first have to show this point. Now this point is where the beam experiences the most bending. Why? Because out of all our bending moment calculations, this one is the most in magnitude. Right, so you first draw, seeing that point B comes after this critical point, right? You draw So we're gonna draw a line. It's curvy. There we go. Right, you draw a parabolic line, right, which shows that in this span of the beam, you have a UDL. Right, now from here to where the beam experiences the most bending, right, that is where you have your 100,227. Right, kilonewton meters. Right, and then from there, you now have to show the bending moment at point B. Now at point B, the bending moment is at 67,5, which is lower than this. So that point is say, let's say here. Say that point is here. Right? Now, because in this span of the beam, we still have a UTL, we have to show that by still representing this as parabolic. But now seeing that it is moving from maximum to something lower, right? Your parabola must show that it is decreasing at this point. So meaning you draw something that looks like that. Right? It was increasing here, hence parabolically, you draw a curve that indicates, right, that this is the plus side of the parabola. And then from here to there, it is decreasing. Hence, you have to draw something that indicates parabolically that the bending moment diagram is decreasing from here to that point. And that point is the 67,5 kilonewton meters. All right.
Sir, sorry, sir. Can you please explain how? I think I missed how you got the 67,5.
How I got 67,5? Or how
Yes,
I draw
sir.
it?
How you got it 67,5? Is the for it's supposed to
Remember,
be
remember that we calculated this. The question was to calculate the bending moment calculations at point B and C. We've already calculated this.
got
So we
you, sir.
calculated
Got
this before drawing the shear force and bending moment diagram. So this is from what we calculated.
you. Okay, thank you.
Yes. Are we together? Hello.
Yes.
Yes,
Yes.
sir.
Yes, sir.
Right. Remember that the bending moment calculations at critical points, right, before drawing the diagrams, we had already calculated. Right. And then this we calculated because the shear force diagram indicated to us that this here might be a very important point to us. Hence, we then calculated the bending moment at this point as well. Right. Otherwise, we had already calculated the bending moments at this point as well as this point. And we know that at the ends of the beam, the bending moment is 0. Right. So this here is point B. Right. This here is point B. That is why it is important that you draw lines, right, going straight down for each of your critical points. We good?
We good.
Yes, sir.
All right.
Better.
Then now we look at, right, we look at point C. Right. We already calculated the bending moment at C. It is equal to this negative 180. Negative 180 is below the 0 line. Right. This is below the 0 line. But now remember that in this span of the beam, you have a UDL. So you must still
Parabol-
continue with drawing a parabolic shape. Say 180 is here. Let's call this negative. Call this. Yes.
In your previous video, or in one of your videos, I cannot remember now. When the value is that 180 is going below the 0 line, then you change the shape of that parabolic to the other way around. So it's
Yes.
curving the other way.
Yeah, that is true. But seeing that this point, right, we draw from here to there, you don't necessarily have to show that. In fact, if you think about it, if say you had to draw a point, right, if say we moved, say our bending moment from here to some point here was negative, right, what you were going to do was, this is what we're going to do. You're going to draw a line going like that, right? With, or how we represent the bending moment below the 0 line, right, is we take the convex approach, meaning that when the bending moment is such that it is decreasing, right, this is how you show that the line is parabolic, but taking a convex as opposed to a concave type shape. And when it is increasing, but from below the 0 line, then how you show that is you draw a line like that. Do you see what I'm saying here?
Okay, yes, I'm watching.
Right.
So-
it's unlike above the 0 line. Above the 0 line, it just takes a normal parabolic shape.
Yeah.
Right. Whereas below the line, right, below the line, if it is decreasing, right, this is how you draw it. And if it is increasing, this is how you draw it. Hence, I'm saying below the 0 line, we take the convex approach of drawing or of showing the parabola or a parabolic curve. Now, if you look at this line, right, this line being below the 0 line, right, it takes this shape anyway. That is why you would leave this exactly as it is. You see what I'm saying?
Sorry, sir. So basically, you're just saying if it were to be starting with a negative number, we would have started it with a curve to the other side.
Yes. Right. And it would look something like this, something like this. Right. So below the 0 line, that's decreasing, that's increasing. Nah?
Yes, sir.
Hello?
Yes, sir.
Yes, sir. Yes, sir. Yes.
Right. So now we have considered all critical points from A to C. All right, the only critical point left is point D. And we know at point D, it goes back to 0. Now, between C and D, there's no UDL. And the way you show that on a bending moment diagram is by drawing a diagonal line. So you just draw a diagonal line going from there back to 0. And this becomes your bending moment diagram.
Sorry, sir.
Uh-huh.
Sorry, sir.
Yes.
Yes, on the if you notice on the question, we got asked to calculate the bending moments on B and C.
Yes.
And then as we proceed, we ended up seeing that there is a necessity for us to calculate bending moments for
X.
point C. Yes, and then for point X, and then we did what the bending moments for point X. Is it required for us to calculate to show the calculations of the bending moment of X, or you can just do it on your rough of piece of paper on the side,
So the value of X you
and
can
then
draw.
you just show it on the spreadsheet.
It is important that you show it here. But now take note of this. All right. Now we drew the shear force diagram and bending moment diagram, right, for context, right, so that we cover everything under the sun concerning beams, right? So that's to say, for this kind of question, where they say calculate the reactions and calculate the bending moments at B and C, right? You would simply do all of this and end at that point. Only in cases where you've been asked to draw the shear force diagram and bending moment diagram would you then have to calculate this point and show it on your calculations as well. Right. So if you've been
Okay,
asked
so thank you.
to draw the shear
Thank
force
you,
and
sir.
bending moment diagram, or you've been asked, because sometimes they will ask you to even determine the what is this, the maximum bending point, right? But whether you've been asked to calculate the maximum bending point, as long as you've been asked to draw the shear force diagram and bending moment diagram, right? And it just so happens that the shear force diagram crosses over, right, like this, then you have to determine this point or the bending moment of this point, and you have to show it.
One more question, sir.
Yes.
Can you please go up on your sketch?
Up or down?
There, sir.
Or
No,
here?
up. Yes, here on at the beginning. Yes. Here you got the critical points, and then on your critical points, for instance, or at B, you got another point that you marked there with yellow on the right hand side and on the left hand side. I just want to be clear, what is the purpose of us having those points that we mark there?
You mean these orange ones? These ones?
Yes, sir.
So those are just sections. So the sections, they help you in drawing the shear force diagram. Remember, in drawing the shear force diagram, I said you must draw sections on the right-hand side of each of the critical points, and then draw another section on the left-hand side of a critical point where you have a UDL on the immediate left of it. So these lines that represents those sections that we use in drawing the shear force diagram. So these ones here, these are not forces. Those are not forces. Those are just sections that you use, right, in calculating the shear forces on the left of each of the sections.
Okay, sir.
All right. If you don't remember, if you need a reminder, just go back to when we were drawing the shear force diagram when I've uploaded the video.
Okay, cool, sir.
All right. Any more questions? Right. If there are no more questions, that is how you would approach such a question on beams. That is how you approach a question on beams. If you are required to calculate the reactions as well as draw the shear force and bending moment diagram. Right. In the past, students used to get away with not calculating the maximum bending moment. Right. But the new examiner, the guy wants you to calculate that thing. So there's no more getting away with it. So make sure that you understand how to essentially do everything under the sun regarding beams, right? From calculating reactions, knowing how to draw the shear force diagram, knowing how to draw the bending moment diagram, and then understanding what the shear force suggests at which points, right? Right, like I said, that with the shear force diagram where it is equal to 0, it is at those points where the beam is likely to experience the most bending. Hence, you need to calculate the distance, right? You have to calculate the distance at each of those points, right? If it happens that the beam or the shear force diagram crosses over at a point that wasn't previously a critical point, then once you've calculated the measurement of that point from the left-hand side or right-hand side, you then determine the bending moment at that point, which will then tell you if that is where the beam experiences the most bending or not. Are we clear?
We
Yes,
are
sir.
clear.
Yes, sir.
Any more questions?
So for test 1, will there be requirements to know definitions, like questions where you need to define the definitions?
Definition? Nah. No.
Can you see the scope in the group?
I've already given you the scope. Kinematics. So that's relative velocity. What's the other one? Resulting velocity, projectiles, and then beams. That's the scope.
Thank you, sir.
Right, with beams, if you do this, if you did the one that's on my videos, and then you do this one as well, then you should be fine. With projectiles,
Okay, sir.
The kind of problems that you can expect is where you are given the angle. Right, you are given the angle, you are given the velocity, and then you're asked to calculate whatever between the range, time, all of that. But those are the kind of problems you
Sure.
can expect under
Thank you,
projectiles.
sir. Thank you, sir.
So can we set up our own formula sheet for the test?
No. You
So
cannot.
for the test tomorrow evening for the online, so you just print the cover page
Tom-
and
Tomorrow evening. Tomorrow evening
for the online.
Meccano.
Oh,
But
sorry,
tomorrow it's only
Macan.
Meccano. Yes.
Oh, so the same principle basically.
Same.
So okay.
With the cover
So,
page, you don't
sir,
necessarily have to print the cover page if you're writing online. Right? You just need to populate it, and then once you are done writing and you scanned your what is this? You scanned your test or your scripts, then all you do is you just attach that thing.
Okay, so will you be sending it
Unless
over WhatsApp?
over WhatsApp, yes.
WhatsApp, or will you have it like this? You share your screen, and
No, I'll
you
have it
have
over
our video on
WhatsApp.
over WhatsApp, and then our video must be on Teams, basically.
Yes.
Okay.
Sir,
Yes.
are you saying you're not gonna provide us with formula sheet?
The